What are gravitational waves, and how can spinning stars known as pulsars help us detect them? This episode, University of Manchester astrophysicist Dr. Michael Keith discusses a discovery that's giving astronomers a new way of observing the universe.
My name's Dr. Michael Keith. I work at the University of Manchester, studying pulsars and gravitational waves. And my main research area is doing pulsar astronomy with the Lovell telescope.
Awesome. Pulsars and gravitational waves is sort of the two key things we're going to be talking about today, aren't they? Because we're sort of, at the time of recording, we're off the back of a pretty big announcement last week involving gravitational waves. So, I think the obvious thing to do at the start of the podcast is to just try our best to sort of, can you sum up for me and indeed our listeners, what exactly are gravitational waves?
Yeah, so, in the simplest sense, which of course is very difficult to visualize, gravitational waves are ripples in gravity. So, in our everyday life, we see light, which is ripples in the electromagnetic field. Of course, to us as humans and our brains, we don't think about this as being ripples in a field. As physicists, we spend our time thinking about this, but in a similar way that the electric field can have light, which we're quite happy to accept, the gravitational field can accept these gravitational waves. And of course, gravity, according to Einstein and general relativity, is really a distortion of space-time, the kind of sort of the underlying fabric of the universe. And so these gravitational waves act kind of like ripples in space-time. But in some senses, it's no different to just the amount of gravity going up and down in a periodic way. But it's like nothing we experience on Earth, right? We have no way of experiencing this in our everyday lives.
Yes, I was sort of, when I was trying to visualize it myself, I was sort of imagining, can you sort of draw a parallel with like sound waves, like the echo of something colliding, or of two things colliding?
Yeah, I think that's right. So, just as my voice travels to you as a wave through the air, the gravitational wave travels from across the universe, as a wave through space-time, and in the same and similarly how it the vibrations of the air affect your ear in order to hear me. The oscillations in space-time affect how we experience space and time. Right, objects can appear as if they're moving closer and further to each other, or moving faster or slower, depending on exactly how you want to visualize your space-time. I think you can draw an analogy in that way.
I think most people will be aware of gravitational waves as being something that happens when, for example, two massive objects like two black holes collide. How do astronomers actually detect those ripples in space-time from massive objects colliding?
Right. So I think in a way that's a little bit of a misconception that the gravitational waves are caused by the collision. Gravitational waves are caused whenever you have massive objects. So by massive, I just mean objects that have mass, right? Moving around each other, right? So whether you have even just in your back garden, waving a couple of tennis balls around, in theory, you're generating gravitational waves. Of course, it's immediately lost to the universe, as nothing meaningful happens from that. But as soon as you have these massive things moving, their gravity is a little bit of that energy is being radiated outwards. And of course, when you have something moving very, 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 very massive, moving very, very quickly as it's about to collide, you do, of course, get a massive spike of gravitational waves. And that's what the telescopes like LIGO are seeing, right? They're seeing this big energetic spike in gravitational waves as these black holes or neutron stars go through the last moments of their existence.
So what can studying gravitational waves tell us about the universe?
So gravitational waves, it's a bit like a sixth sense for astronomers. Admittedly, in some ways, we only have one other sense, which is to look at the universe with our eyes, right? So we're doubling the number of senses we have to see the world, right? Up to now, from the very first people looking at the stars, every piece of information that's come to us has come in the electromagnetic spectrum, either by literally looking with our eyes or using, an optical telescope in space like Hubble, or now infrared telescopes in space like the JWST, or big radio telescopes like the Lovell telescope and all these other telescopes around the world, seeing in radio energies. But it's all coming on the same carrier, right? It's the same sense, just spread out. Now we have a really, really new way of looking at the universe. And currently I think our sense, it's still at the very early days and it's a very dull sense, but it is totally new, and it's giving us a parallel stream of information that tells us about, directly about the masses of objects and things like that. And actually, in astronomy, you can't go out and weigh a black hole, right? When we say we know this star is a certain mass, almost always that's, according to our very good understanding of how stars work, when we look at this star, we think, well, it has certain properties, and we compare it to our sun, and we compare it to other things we do know the mass of, and therefore we say, well, it has this mass. But actually, it's very hard to measure these masses, and so by directly seeing something about how the mass is behaving and what's happening to it as it's moving around in space, we have this totally new way of learning about all these objects, but particularly the very massive ones.
Amazing. I mean, that sort of brings us on to talking about the discovery that you and your colleagues announced last week. Well, yeah, I suppose. First of all, just tell us about the discovery, because as far as I understand it, it was regarding a sort of like a new type of gravitational waves that haven't been detected before.
Right. Yeah. So as with sound or with electromagnetic light, there's different pitches, right? You might have a very high frequency sound, you might have very, very low frequency sound. And, in that analogy, what we've seen to date is a pretty high frequency sound, right? It's this sort of chirp of the black hole in its last moment, right? At a very high frequency. What we've announced last week was this discovery of these very, very low frequency gravitational waves. So in fact, these are gravitational waves that are washing over the Earth with a period of years, right? And that means they have wavelengths of light years. So this is sort of ultra low frequency gravitational waves, and therefore it's looking at different types of objects. What we think we're seeing is orbiting supermassive black holes. So these are billions of times the mass of the sun, going around each other in the centers of distant galaxies. And these supermassive black holes are indeed stirring up, gravity and stirring up space-time, and the signal from that is radiating across our whole, across our galaxy. And so it's almost like, we're sort of in a regime where we're seeing things that affect our galaxy rather than just affecting, a little detector.
I mean, at the start of the podcast, you mentioned that your sort of two areas of expertise are pulsars and gravitational waves, and it's actually pulsars that enabled you to make this discovery, wasn't it? This detection.
Right, exactly. So pulsars are a very exotic kind of star, right? So these are the stars at the very end of their lives. They've gone through a supernova, and what's left is this core of ultra dense matter. It's the core of the star is completely collapsed, and it's barely hanging on before it collapses into a black hole. Its density is something similar to the density of an atom, right? And also, as it collapses, it ends up spinning very, very quickly through conservation of angular momentum. It's something you might experience if you've ever watch an ice skater as they if they want to spin fast, they bring their arms in and it spins them up. Well, if you go from something the size of a star to something that's the size of Manchester, right? These things are only a few kilometers across. You start spinning very, very quickly. And in fact, the ones that we're looking at, they go around at 500 times a second, which I think is something like 30,000 RPM. It's the kind of thing, if you put on your blender on top speed, that's what this star's doing, right? So it's a very, very exotic object. Now, why is that useful? because it turns out if you get something that's very, very massive, very dense, and you spin it around very quickly, it can act a bit like a clock, right? It's got so much inertia and momentum that it will just keep spinning, and it's very hard to make it do anything other than spin very regularly. And conveniently, these kind of stars also shoot out sort of jets of radio emission along their magnetic poles, and this acts a bit like a lighthouse. So it sweeps across the Earth, and we see a bright flash as it's sweeping across the Earth, and so we can count the ticks from these pulsars, and that gives us this clock. Okay, so why is a clock useful? Well, if what you're interested in is studying ripples in space-time, one of the things that rippling space-time does is it changes the rate at which clocks go. And so by looking at these pulsars, we can see, well, is the clock of the pulsar changing? And if we see the clocks of the pulsars changing in a way that they're all kind of changing in some kind of characteristically similar way, we can kind of infer that, either the universe is conspiring to trick us, or there's some underlying signal that is causing this correlated change in the clocks. And so, of course, our simplest hypothesis is that actually, yes, there's a gravitational wave passing over the Earth, and that is causing it to appear as if these clocks are, these pulsars are talking to each other and working together to give us a signal. But actually, of course, it's the gravitational wave effect that we're measuring. And so this is, it is a very long-term experiment in order to do this. We're looking for waves that have periods of years, and so we need to observe the clocks for years. And in fact, for these experiments, we've got 10, 15, 20, 25 years of data now. And so it's only by looking over these very long timescales that we see the sort of signature of these gravitational waves showing up, and that we can start to now, at this point, start to say, hey, I think we really have detected something, and then go on to try and understand what it is that we're seeing.
Yeah, that was one of the things I was going to ask you was, if you take like a clock, in order to notice it changing, you've got to know what it should be. So,
right.
So
Yeah.
So do you have to observe the pulsars so that you can see how they should be operating, and then you can determine how they're changing?
That's exactly right. And in fact, in some ways, that's where I fit into this collaboration personally, is that my experience is trying to understand these pulsars, and to be able to predict how they're going to behave. Now, it is true that unlike something like LIGO, where you generate a signal, you've made a signal and you're looking at how that signal gets affected. We have a natural signal. And so, yes, we don't know. The pulses from the pulsar don't come with the time written on them, which is very inconvenient. But what we can do is see how the rate of the clocks changes, or equivalently, you can think of it as the ticks coming a little bit earlier than you expected. And so, yes, by studying the pulsars, we can get a very good prediction of when they will arrive. In fact, if I had a bit of time sitting on my computer, I could tell you when is the next pulse from this pulsar going to arrive to, 100 nanoseconds or something, right? We can absolutely know very precisely when these things are going to happen. But I think it is fair to say, though, that when you're using these natural sources, they are quite complicated, and the physics of these pulsars is extremely complicated, right? These have the strongest electric fields and magnetic fields in the universe. A lot of the physics that assumptions that we rely on, particularly in our everyday life, certainly just don't make sense there, right? So it is not easy to be very confident about this stuff, and predicting and modeling what are the kinds of things that a pulsar could do compared to what the gravitational wave could do is part of the game of this thing, right? Is how you actually go from, well, I just see a load of ticks from a clock, to being able to say, well, this is, now I understand what the pulsar's doing, and hence I now can say, what is the gravitational wave signal doing?
Awesome. I mean, just when you're talking about sort of black holes at the center of galaxies, as I understand it, these supermassive black holes at the centers of galaxies, there's a sort of isn't there sort of a chicken and egg question? We don't know if galaxies form around the black holes or if the black holes form within already existing galaxies. And if that is indeed like a sort of an unsolved conundrum, are observations like these going to help solve the mystery?
Yeah, I think that's right. Certainly, an interesting thing is, how do galaxies form, and how do these supermassive black holes form and grow so big? It is a good question. Do the black holes start off massive, and indeed, as you say, maybe galaxies grow around them, or galaxies grow in the same gravitational wells as them? Or is it all done by merging, or is it done by, you start with a small black hole and it, lots of the matter of the galaxy ends up falling into the black hole? I think there are a lot of questions, and certainly there are a lot of people who spend a lot of time trying to make sense of all this stuff, right? And there are some really good theories, and I think there's, from electromagnetic radiation and looking, things like Hubble and JWST, where you can look back in time and see these early galaxies, you can definitely start to say some things about, okay, how did galaxies form? So I don't want to say that, these are the results that will change completely our understanding, because I think that would be unfair to all these other wonderful experiments. But certainly knowing there's, this much black hole, the simplest thing that we can do is say roughly how many black holes are merging right now, right? What is the rate at which these black holes merge sort of through the universe? Do we think that can explain all the growth of black holes? If every black hole merger is because a galaxy merged, right? I mean, where do these black holes come from to merge in the first place? They were in galaxies, and the galaxies merged, and then the black holes sunk to the middle, and they go around each other, and then they eventually merge. Can that explain everything that we see, or are there other things? And I think at the moment, there's sort of, in some way, the surprise is that actually the gravitational wave signal seems quite strong. There seems to be lots of black hole merging going on, if these results are to be completely believed, and that's kind of interesting, right? There's this process that we didn't really know whether it existed or not, turns out to be quite important, because clearly it's happening all the time. So I think it will. It's very early days, but I think it will start to be a really important thing in our understanding of how galaxies form and black holes form.
Actually, just coming back to the pulsars. From reading the story, I believe there were 25 pulsars were observed. So how did you actually decide which pulsars you were going to use for the survey?
Right. So within our European collaboration, we observe 25 pulsars. Actually, I think we observed slightly more than that, but we selected the 25 best ones to do our analysis. And really, that's what it comes down to. It comes down to which are the stablest clocks, which usually means the ones that are rotating the fastest. There's also a particular kind of pulsar that is more stable than the typical pulsar. We know something like 3,000 pulsars now. Most of those are young and hot-headed, and they do wild things, right? They are in their teenage youth of being a pulsar, and there's all kinds of stuff going on. The ones that we want for this experiment are the very boring old men of just droning on through the universe, not doing anything interesting. And so we select the pulsars that are in some ways the least interesting from the pulsar point of view, because they're the most stable clocks. They're just going around doing their business.
So presumably in the future, you might want to follow up if possible with like either a brand new batch of pulsars, or would you want to just add to the existing batch? Right.
So absolutely, we want to look at more pulsars, and I think there's two things that are going to happen to make that happen. Right. One is what I'm talking about at the moment is what we're doing within the European pulsar timing array, but there is also people who doing the same thing in the United States and Canada, which is the Nanograv collaboration. And they, in fact, have got 60-something pulsars in their data set. It's a very, very nice data set. There's a group in Australia with the Parkes telescope, and they've got something like 20 pulsars. There's a group in China. There's a new telescope in South Africa called Meerkat that's just started taking these things. And you can't quite just add up all the pulsars because many of the best pulsars we're all looking at. But we're going to bring together all those things. And I think that is really going to solidify this detection and help us to really understand what it is that we're seeing right now. But the main thing for the future is going to be this new telescope called the Square Kilometre Array, part of which is being built in Southern Africa. And that, one of the main science goals for that telescope is to do this experiment properly, right? To go from the ground up, build a very big radio telescope. It has the flexibility to do lots of, wide frequency coverage and, all the good stuff you need. It's got very good clocks inside and all this kind of thing. And that is going to really, I think what's going to be doing the real gravitational wave science, right? Right now, we're making a detection. We're saying something perhaps about the amount of signal that we're getting. But to really study this stuff, this new telescope, the Square Kilometre Array, that's going to be the thing that I think will change the game in terms of doing the actual science.
From memory, isn't that sort of being headed by the University of Manchester? Because aren't the headquarters at Jodrell Bank?
So the headquarters are at Jodrell Bank, but it is not run by the University of Manchester at all. The headquarters of the Square Kilometre Array at Jodrell, because it is a kind of radio astronomy heritage site, I think, and they have access to lots of people who know about radio astronomy there. But this is a completely global thing. In fact, it is a kind of international organization. So it's in some way not even part of the UK in some funny way, right? It's a bit like the European Space Agency in the sense that it's this kind of international organization that happens to be physically located in Manchester.
Could we use the gravitational wave and pulsar technique to sort of learn about the supermassive black hole at the center of our own galaxy? Is that of interest, do you think, to radio astronomers?
So I think we can certainly learn about perhaps the types of things that went into that that black hole forming. I mean, fortunately for us, the black hole in the center of our galaxy is actually quite a boring black hole. It is not in a binary. It does not have massive jets of radiation coming off. It is not doing anything wild. It's very convenient because, you may not want to be in a galaxy where the black hole in the middle is doing completely wild stuff. It's probably slightly unhealthy. But yeah, I mean, look, we want to know about ourselves. I mean, we want to know about our galaxy. And learning about how galaxies form is definitely on the cards for this stuff.
And so, presumably, are you still working on this study? Is there still sort of data to go through and things to be learned, or have you extracted all the information from this study and it's sort of on to the next one? Do you think?
I think we're still working on this. I mean, I think, as I said, the big thing is to bring together the international community, and even from the side of learning about the pulsars, I think we can do better on this stuff, right? And again, by combining with our international colleagues, I think we will learn more about what the pulsars are doing, and that will help us to really focus the picture on the gravitational waves. But also, I think we really are at the beginning of this kind of new age of gravitational wave astronomy. We published, I think, on Thursday, we put out all these papers. And on Friday, there was something like 20 papers that people had written about what it all means. And of course, everyone seems to think what it all means is something different and wild. And, we're at this sort of period where, now the theorists can have fun trying to interpret what's going on with what's going on. And at some point, we'll work it out and we'll settle into a new picture of what this stuff is. But yeah, right now, I think, we're going to go back to the the data and keep going on it because the data keeps coming. But now, the new thing is the physicists and the theoretical people have something really to get their teeth into. I think up to now it's all been a bit if this then maybe, and now there's, hey, we've got an actual thing. Let's go and see if we can make sense of it.
Fantastic. Well, Mike, thanks very much for coming on the podcast and speaking to me and sharing the discovery. It's amazing. I mean, obviously, I and the rest of our listeners will be waiting with bated breath to see what happens. It seems like a really exciting field. It's just sort of starting to get going. It'll be really interesting to see what happens. But yeah, thanks for coming on the podcast and getting us excited about it.
Okay, thanks for having me on.